Okay, so let's look at different types of chemical formulas. So essentially, in this notes, we're looking at empirical versus molecular formulas. And what this is going to get at is if you're going to describe the form of a compound, there's two ways to look at it, because what we've talked about earlier is empirical form, which is a simple ratio of the elements. For example, water is seen as 2 hydrogens for every 1 oxygen, or sodium chloride, 1 sodium for every 1 chlorine. But there's ways beyond that to describe what's in a compound, because yes, you can talk about the ratio of the elements, but you can also talk about what the compound actually contains. Now, it should really be really clear, for ionic compounds, there's only one formula, and that is the empirical formula. So for ionic compounds, it's because in ionic compounds they exist as crystals, so that means sodium chloride crystals can be small or large, which means that they can contain varying number of atoms, so the total number can vary from sample to sample of an ionic compound, but the ratio remains the same. So the empirical formula works for ionic compounds always, and it works for non-ionic compounds also, which is to say molecular compounds, but sometimes molecular compounds need a different kind of formula to describe them, because molecular compounds sometimes there's a difference between the ratio of the elements in the chemical and what's actually there. And these are good examples right here. Glucose sugar contains C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens. That's how many atoms are actually in each molecule of glucose sugar. However, if you take the ratio, that means divide these down to as far as you can, divide these all by 6, in other words. This divided by 6 becomes 1, this divided by 6 becomes 2, this divided by 6 becomes 1. So this is what's actually there, and this is the ratio. So the empirical formula is the ratio between the elements in the compound, and a molecular formula tells you how many of each atom are actually in each individual molecule. So again, molecular and empirical formulas may or may not be different for molecular compounds. However, for ionic compounds, there is no molecular formula because ions don't form molecules, so only empirical formulas apply for ionic compounds. So examples of those, more examples include these here, where butane is composed of 4 carbons, 10 hydrogens, which comes down to a ratio of 2 carbons for every 5 hydrogens. So again, it's the difference between what's actually there and the ratio between the elements. This isn't to say that every non-ionic compound is like this, because after all, there is water. It's a ratio of 2 hydrogens for every 1 oxygen, and that's what's actually there. Like the water molecule really is 2 hydrogens and 1 oxygen, so that would be a case where the empirical and molecular formula is the same for this particular example. So let's see, are there any other examples? I think that pretty well covers that kind of an idea. So just kind of beware of that possibility. Some molecular compounds have an empirical and molecular formula that is the same. Other molecular compounds, such as these, the empirical formula is different from the molecular formula. Okay, so if you're going to actually calculate empirical formulas, that means you are going to be finding a ratio between the elements. So this is kind of the outline of how that happens. Take mass of the elements, convert to, well, okay, that's actually if you have percent composition. So if sometimes you begin the percent composition, which is you convert that to grams, or you're given grams and you start with grams, convert it to moles. That way you're comparing number of elements in moles is how many there are. And then you calculate a ratio, and that tells you the empirical formula. So here's what it actually looks like. So if you look at this particular example with 4.151 grams of aluminum and 3.692 grams of oxygen, we have to understand you cannot take a ratio between these because this is the mass. It's not comparing what a formula shows. A formula is not a ratio of masses, it's a ratio of numbers of atoms. So that is why each of these is converted to moles, because comparing the grams doesn't tell us a thing. But comparing the number of atoms will tell us what the formula is. After all, mole is a number. So This tells you how many aluminum atoms there are. This tells you how many oxygen atoms there are. So how do you compare them? The answer is you make a ratio. So that means you take the smaller out of the two numbers of moles, and you divide each of these by the smaller number. So being that 0.1539 here is the smallest, you'll notice each one is divided by that number. We leave no units here because we're doing this for the purpose of making a ratio. So I leave no units in this number, allowing the units originally here, moles of aluminum, to remain, moles of oxygen remain. And then dividing these numbers makes 1, dividing these numbers makes a number that comes out to something close to 1.5. The number may not be exactly 1.5, might be 1.499 something or other, but if it's close to 1.5, you call it 1.5. Because here's the thing, we're trying to figure out what the ratio is. So we're saying, okay, this is a 1 to 1.5 ratio. So it's 1 aluminum to 1.5 oxygens. Now, in this case, what I'm saying here is that 1.5 to 1 ratio is the same as 2 to 3, so that's why if it's 1 aluminum for every 1.5 oxygens, that becomes 2 aluminum for every 3 oxygens. This and this is the same ratio, and a 2 to 3 ratio is a 2 to 3 ratio as seen in the formula. Now, wait, how do you know that? How do you know to turn 1 to 1.5 into 2 to 3? The answer is, if you weren't able to come up with this, turning this into this off the top of your head, the answer is times it by 2. If you see a ratio with a decimal in it, try timesing it by 2. Hopefully it'll make it into two nice round whole numbers. If that doesn't work, try timesing it by 3. If that doesn't work, try timesing it by 4, and so on and so forth. And that is what you do in order to take something that involves a not whole number and turn it into a ratio that does involve whole numbers. In this case, timesing it by 2 worked well enough, so we didn't need to try timesing it by 3 or 4 or 5 or 6. So I'll even make that note. Multiply by 2 to get a whole number ratio. Okay, I make that note on here. You, the viewer, would probably do well to make that note on your page too. Again, if 2 doesn't work, try bigger numbers. If this doesn't work, try bigger numbers. There you go. So you times it by 2, see if that gives you whole numbers. If that doesn't work, try timesing it by 3. If that doesn't work, try timesing it by 4, etc. So, last thing, why 4 sig figs here? Well, technically 4 sig figs here, 4 sig figs here, but actually sig figs don't matter here. Sig figs don't matter. Now, why do they not matter? It's because this is not the final answer. So that's why sig figs don't matter, because it's not the final answer for that and for that. That's the final answer. But being that this is a ratio, that means it's just whole numbers. You need just whole numbers, that's all. When you deal with ratios in a chemical formula, it needs to be whole numbers. So the whole concept of sig figs just doesn't really apply to these particular kinds of questions. So, as you mentioned that, there are questions on your practice paper that look just like it. I recommend practicing with them in order to get a good grip on how these work. But you can look at your practice paper and work with these later if you like. Go and pause this video and work on them. But anyway, here I move on to explaining the next question. All right, let's get this out of the way. So, sample of vanadium metal reacts with oxygen. Its mass was 0.3546 grams before the reaction and 0.63301 grams afterward. What is the empirical formula of the resulting vanadium oxide? Okay, so in this one, we're going to say, okay, we need a vanadium and oxygen ratio. You're going to have some combination of vanadium and oxygen. So you're going to take the number of moles of vanadium, find the molar mass on the periodic table, and use it to convert to moles of vanadium. Because again, if you're going to find a ratio, in order to make a formula, that's a ratio between the number of atoms, which means it must be done using units of mole. So that's why we do moles of vanadium. But what about oxygen? Well, this isn't your number of grams of oxygen. This is vanadium alone. If it reacts with oxygen, oxygen is matter. It is atoms. It has mass. So this is the mass that is combined vanadium plus oxygen. So this is vanadium only. This is vanadium plus oxygen. So that's the combined mass. You got to do some subtracting in order to figure out what the mass of oxygen is alone. Because we need to compare the mass of vanadium and oxygen. And that's not oxygen, that's oxygen plus vanadium. So that's what's going on here. Here what I'm doing is I'm taking this, the combined mass, subtract out vanadium to get oxygen only. So this number minus this number equals this number, which would be the mass of oxygen only, 0.2784 grams of oxygen. And you take that 0.2784 grams of oxygen divided by, well, times 1 mole of oxygen divided by 16.00 grams of oxygen to get moles of oxygen. So that's really important. Make sure you understand what these numbers, if dealing with the question of this, you want to make sure you understand what these numbers are standing for. So once you get moles of vanadium and moles of oxygen, now you can divide both of these by the smaller number, which is, this is the smaller number, so divide both numbers by these, which means for every 1 vanadium, you got 2.5 oxygens. Now in a formula, vanadium is a positive metal, so it goes first in the formula. Oxygen is a negative anion, it goes second in the formula after the positive thing. So that's why vanadium first, then oxygen. If it's a 1 to 2.5, let's see, I'll times each of these by 2. So times 2 equals 2, times 2 equals 5. So that's where I get the 2 to 5 ratio, and that's why the formula is V2O5. Okay, so given that, again, there's more problems to practice with, but now for the next question. How do you deal with it if you have percent composition? The answer is at once simple and, well, a little long. Simple in the sense of once you deal with these numbers, the process becomes exactly the same. Long in the sense of you have 1, 2, 3, 4 elements to deal with. So that's it can, in this particular case, it's a fairly long calculation, doable, but it can be long. So if you're given percent composition, you essentially will treat it like you have 100 grams of the sample. So we'll say 65.02% platinum. Fine, we'll just call it 65.02 grams of platinum. And same for the other elements. 9.34 grams of nitrogen, 2.02 grams of hydrogen, 23.63 grams of chlorine. We just treat it like we have a 100 gram sample. That way we make these numbers nice and easy. Then, once you have the grams, it becomes exactly like the previous question. You convert each of these to moles. Now, I did, for the sake of simplicity, I did it this way on the note handout, or on this slide. But understand that this is the equivalent of 65.02 grams of platinum times, for every 1 mole of platinum, or I should say the mass of 1 mole of platinum is 195.08 grams of platinum. And that equals 0.3333 mole of platinum. Okay, so I'm just like doing this to point out that this is the equivalent of this. So we're not doing anything differently here. This is all the same. And the same idea applies to each of these. It's just the only reason it looks like this is for the ease of putting it onto a PowerPoint slide. Okay, so given that, now, having done the same as before, you've converted each of these to moles. Convert this to moles, convert this to moles, convert to moles, convert to moles. All right, once you've done that, oh, by the way, we should all know that these are diatomic elements, but because they're not pure, they're part of a compound, you are not timesing the mass by 2. 1 nitrogen, mass of a nitrogen. 1 hydrogen, mass of 1 hydrogen. Anyway, aside from that little aside, once you have converted each of these to moles, same process. You divide all of them by the smallest number. Let's see, that means this one. This one's the smallest number. So divide each of those numbers of moles by the smallest number. So that's where 1, 2, 6, 2 comes from. Now be aware, it may not come out of the calculator exactly. It might be like 6.1 or 6.01 or something like that. If that's the case, you just round it to the nearest number that seems reasonable. So 1 to 2 to 6 to 2. So this is a ratio. And the question is, can it be simplified down? The answer, not really. If you got 1, then you can't really divide it by anything. It has to be whole numbers. So if you got 1, you can't simplify this. So that's why the final answer will then simply be, if you got 1 to 2 to 6 to 2 ratio, a 1 to 2 to 6 to 2 ratio, the formula is 1 platinum, 2 nitrogens, 6 hydrogens, 2 chlorines. For this particular example. Now, how did I know to put in that order? Well, a little aside about how to put the formulas together. For some formulas, like these, which are simple, it should be obvious that vanadium is a metal. It's positive. Cations go first in a formula. Anions go second. Same thing for one of the previous examples here. Aluminum and oxygen. It should be clear. Aluminum goes first in the formula. Oxygen goes second because positive thing goes first, negative thing goes second. Now, if you have a formula with multiple chemicals where you wouldn't have any way of knowing that, especially an unfamiliar compound, we will generally do the favor of putting it in the order that we want you to put it in when you do your final formula. So we're looking for platinum, nitrogen, hydrogen, chlorine in that order because you, the viewer, would have probably not be familiar with this chemical and therefore not have any way of knowing how it goes together. So we'll tell you for these complicated ones where you wouldn't know. But for simple ones, like a simple cation and an anion, expected to be able to know that the cation goes first, the anion goes second, and put that in order without prompting. Okay, so that's how you deal with the empirical formula for a variety of different compounds. What about the molecular formula? So how do you deal with the difference between, okay, so empirical formula is simply finding a ratio. What if we want you to tell us, what if we want you to calculate how many atoms are actually in the molecule? It's actually not that different a process. It's actually the same thing, but with one extra step. Okay, reminder, empirical formula is what's actually in the molecule. This only applies to molecular compounds. The molecular formula is what's actually in the molecule. It only applies to molecular formulas. The empirical formula, I think I may have misspoken earlier, the empirical formula is something that applies to all chemical compounds, but the molecular formula is going to be unique to molecular non-ionic compounds. And sometimes molecular formula and empirical formula is the same, like in H2O it's the same for the compound, it has the same empirical as the molecular formula. In other compounds like these, the empirical formula is different from the molecular formula. So anyway, with this molecular formula calculation, what do you do? Okay, nice example here. If we give you this, the empirical formula already, and this, you actually have everything you need to find the molecular formula. So once you find the empirical formula, you're going to do a little comparison. You're going to find what we call the empirical formula mass. You're going to say, if it's 2 phosphoruses and 5 oxygens, you can take your periodic table and the mass of 2 phosphoruses, there's each phosphorus times 2, there's each oxygen times 5. You can add up what the formula mass would be, the empirical formula mass. So if you add these up, that adds up to 141.94 grams. But wait, we said the actual molar mass is this. Well, that's all the information you need. So what you do is you take the molar mass, which should be the bigger mass, and divide by the smaller mass so that you get a whole number coming out, or at least a number bigger than 1, or greater than or equal to 1 anyway. And this is not exact, but it's approximately twice as big. So, oh, if the molar mass is about twice as big as the empirical formula mass, that means you can take the formula and times it by 2. So that means 2 times 2 is 4, 2 times 5 is 10. So this would be the actual molecular formula right here. Twice as it's because the actual molar mass is twice as big as you'd expect from the empirical formula, which is why the formula is twice as big as the empirical formula. So that's all you have to do if you're given the empirical formula already, but of course that doesn't always happen. If you're not already given the empirical formula like this, well, then it becomes necessary to find the empirical formula first and then convert that empirical formula to a molecular formula using this information. So the empirical formula, well, as a review, if you're given the percent composition, assume a 100 gram sample, so 24.27% carbon becomes 24.27 grams of carbon. We do the same to the hydrogen, we do the same to the chlorine. Convert each to moles in the same way as we did in the earlier example. So you take the grams of carbon, deal with the molar mass of carbon to convert it into moles of carbon. Same for hydrogen, same for chlorine. And once you got the moles, you divide all of these by the smallest number. 1 carbon, 2 hydrogen, 1 chlorine. Again, you got that by dividing by the smallest number of moles. So carbon, hydrogen, chlorine, and you wouldn't know what order those go in, so we put them in the order we want you to put them in. So the ratio of 1 carbon to 2 hydrogens to 1 chlorine makes this the empirical formula. 1 carbon, 2 hydrogen, 1 chlorine. So, finding the empirical formula, you then find the empirical formula mass. So if that's your empirical formula, there's the mass of your 1 chlorine, your 1 carbon, and your 2 hydrogen. I don't know why I did it in that particular order. It doesn't, it's math, right? It's just addition. It doesn't matter what order you add them together, it gets the same answer in the end. Anyway, that's the empirical formula mass. And the original question said that this is the molar mass of the compound. So we see the molar mass is twice as big as the empirical formula mass, which means you got to take that empirical formula and times it by 2. So instead of 1 carbon, there's 2. Instead of 2 hydrogens, there's 4. Instead of 1 chlorine, there's 2. And this is the actual molecular formula. So there's other examples that can be worked on from the textbook that tell you which questions to work with. At least the textbook that we're using as of the year 2019 when this video was made. So that should give you something to work with. Make sure to practice with these in order to master the skills. So cool, there we go.